Okay, so question 71 of chapter 10 starts off this way. See about doing a split screen, but writing might be too small for that. We'll see as I go along. Okay, so here's this ramp. And so pulley all the way up, and then we have this guy falling down like so. So mass 2 is 20 kilograms. Mass 1 up the ramp, 15. And the acceleration is up the ramp like so. Two meters per second squared. See what else. Says 2 blocks are shown in the figure connected by a string of negligible mass over a pulley of radius 0.250. It's the radius of the pulley. A moment of inertia I. Or moment of inertia. The block on the frictionless incline is moving up with a constant acceleration of 2 meters per second squared. Determine T1 and T2, the tensions in the 2 parts of the string. And so the implication, there's going to be torques on both sides. There's a torque over here and a torque provided by this tension. And if you were pulling down the ramp from tension 1, you will notice that that's going to provide this little inset here. So T1 is going down the ramp like so. So it's going to be causing this guy to spin in a counterclockwise fashion. So the torque provided by T1 is going to be positive, and radius R and all that stuff. Okay, so counterclockwise rotations, counterclockwise directions mean that the angular quantities are positive. Positive torque, positive angular acceleration, positive angular velocity, positive angular momentum, which is chapter 11. We'll be getting to that. So we have forces and torques, so it's important that we draw the torque diagrams and the free body diagrams. Free body diagrams should be no-brainers by now. I hope so, but that's why we're going to practice and keep practicing. So T1 is going to go up the ramp like this. FG, which is mg. And it's off axis, so it has components. This is going to be negative m1g cosine theta. And this guy here is m1g sine theta, or the theta is here. Those are the same. No friction, so nothing going down the ramp. But m1g sine theta is, going to be, actually this will be negative, and we'll see by orientation, because, so the acceleration of the system is up the ramp, so everything, all the forces with the acceleration will be positive. So we're going to have our perspective x, y. So this is why this guy here will be negative, actually. So I'm going to erase this. Negative m1g. And if there's any questions at any point, anywhere, even on free body diagrams, don't be afraid to ask. Your silence is death, if that means you have a question. Otherwise, no news is good news. Good. Okay, so that's our perspective out of that. So that's our free body. And then for the other guy, it's pretty simple. I hope. Anyway, so T2 free body wise, okay, is going to be negative because it's going against the acceleration of the system. So for this orientation, acceleration's up. This orientation, acceleration is down. So all the forces moving with are positive. So keeping that consistent, all things consistent there. Next are force equations from the free body diagrams. So we have Fx1 to be T1 minus M1G sine theta equals M1A. And Fy2, because there's only forces in the vertical direction for mass 2. For mass 1, there's 2 sets of forces. I'm going to go ahead and just put that up first. So Fx2 or Fy1 actually. So that's going to be Fn minus M1G cosine theta. But that's not important for us because we don't have friction, but just to label it, just to keep track of it, that's what the forces in the vertical direction for mass 1 will be. And then for mass 2, T2 plus M2G equals M2A. So they want you to find the tensions T1 and T2. Well, T1, you can find them quite easily. You're given the acceleration, you have to solve for it in order to backtrack and get that. But let's get the torque equation first. So the net torque equation, again, we must visualize appropriately where T1 and T2 are. Okay, so T1 is going to give a counterclockwise rotation that we see here. We have 2 forces in the vertical direction because for mass 1, we have these pair of forces in the vertical direction y for this perspective here, because the axis is going to be tilted. So we have x, y. And so we have forces for mass 1 in the vertical direction like this. And then for mass 2, we have the only forces that exist for that is in the vertical direction. So that's why we have 2. The up and down. Okay, so going back to the torque equation there, so we have T1R, yeah, counterclockwise. And then T2R is going to be a clockwise rotation. Is everybody comfortable with that? If there's discomfort, let me know. So T2 left by himself, if you pull down this way, it's going to cause the pulley to spin clockwise as T2 pulls down on the pulley. So that's why he's going to have a negative torque. So T1R minus T2R. And since the whole system moves in the direction of T2, the net torque in the system is going to be clockwise. So the entire spin will be a net torque. The net torque will be clockwise. So negative I times alpha. Okay. Is everybody comfortable with that? So again, R is just going to be rotating in a clockwise fashion. So the net torque in the system will be negative. The torque is negative. Yeah, the overall rotation is going to be clockwise, because even though T1 wants to rotate it counter, it's overcome by T2 because it's a larger weight. And so once we put in our values for T1 and T2 and our values for R, it's very easy for us to get our moment of inertia. So expanding this guy out here, so we have T1R. And alpha is A divided by R. A we know is going to be 2 meters per second squared. And so all we have to do is just solve for we have to solve for our tensions, and then we can get our moment of inertia. And we have our radius already. So this will become T1 R squared. Is T2 R squared equals negative I times A. And A we know, solving for I, and R we know. So it's going to be R squared T1 minus T2 equals negative I times A. Right? So that's what we're going to be working with at the end to solve for I. And you see that the moment of inertia in this context will be negative, but the moment of inertia can never be negative because it's a scalar quantity. It's a property of mass, which is a scalar. So we just make the physical correction to the result for a moment of inertia, which will be negative in this case, but we know it's positive because it's a function of mass, distribution of mass. It's a scalar. So anyway, but so that I don't know if there was any confusion at all on why this is negative, whatever. But yeah, this will be negative because overall rotation is clockwise, blah, 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 blah. And that, yeah, results out. So let's get our T1 and our T2. So T1, we can just take the equation up top. So M1A plus M1G sine theta. Factor out the M1, you can see that this is going to be factored out. And then this is going to be 15 sine of the angle down. So sine of 37, that becomes, I think that's like 120. I guess that 120 newtons for the tension. Never find my calculator. guess that means I use it too much. $118.5. Round it up and 120. Okay. And then T2, similar. You can find it. Let's see. Oops. Okay, so it's going to be M2G minus. So mass 2G minus A. 9.8 minus 2. 20 times 7, roughly 156. Well, wait, that's not quite 7. 7.8. 156 newtons. And so yeah, it all checks out actually, you know, because it's going to be negative. All right, so we got the tensions. Okay. So we take our formula, R squared T1 minus T2 equals I, or negative IA. We've had right here. Then we just divide it. So 0.25 squared T1 120 156 equals negative I divided by 2. So yeah, it balances out anyway. So I was saying that physical correction, sometimes we have to do that, you know, because sometimes the answer will be negative, but we know it's positive because it's scalar. But in this case, it works out. Works out fine. When you do this, you're going to get your moment of inertia to be roughly 1.12 kilogram meters squared. So that one's all right, at least from a few of you. And hopefully the rest of you now can see how easy that is. Any questions? What's the problem there? I was going to give you number 66. That was a nice one. I'll still give it to you. Probably a homework assignment. Because I had done it before. I don't like reinventing the wheel when I do the problems already, but that's a lot. This is a loose piece of paper. I think I threw it out. Anyway, 85, but 66. I'll give that to you, maybe homework. I got time to do 85. Let me see. Let me digest 85 here. Yep. Yeah. Yes. Okay. Okay, so we have a spool of thread consists of a cylinder of radius R1 with end caps of radius R2 as shown in the figure. The mass of the spool, including the thread, is M, and its moment of inertia about an axis through its center is I. Moment of inertia, I. The spool is placed on a rough horizontal surface, so it implies friction there, so that it rolls without slipping when a force T acting to the right is applied to the free end of the thread. Show that the magnitude of the friction force exerted by the surface on the spool is given by that formula. Determine the direction of the force of friction. Okay. So one thing we can do first is take a look at the torques in this situation. We have two forces here providing their respective torques. So you have the force of friction applying a torque that's going to go to the left, or at least the friction force, and then the the tension is going to be pulling with a force to the right, but you know, taking the forces, isolating the forces, we see that friction, if left alone, is going to cause the system to rotate counterclockwise. And tension is going to cause the system to rotate in a clockwise fashion. We take a look at their respective torques. The first situation, we have our net torque. It's going to be the force of friction, that friction force times R2 provides a counterclockwise torque, and then this tension is going to provide a clockwise, and its net tension is going to be equal to I alpha. It's a net, a positive torque in the system. And then if we expand this guy out, we are going to say FR2 minus TR1 equals I A over R2. Because it's going to be providing a clockwise torque, the force of tension T. It's going to rotate the inner spool clockwise. And then taking a look at the forces, they're both in the horizontal direction. T minus F equals mass times acceleration. Okay, let's take a broader look at that. But what I wanted to go back to, I'll say this on the surface, it's hard to see why T provides a clockwise torque. I get the question. But because you know, we definitely got to visualize that going forward. The whole thing moves to the right, moves in this direction. So F is going to provide a, so let's say that R2 comes all the way down. So, I mean, I think we're all comfortable with the counterclockwise by force 1. Even though there's a tension here, it doesn't cause this inner radius to go in a counterclockwise direction, because that would imply that the inner radius, or this inner piece of this wheel, is going to be spinning independently. It's just attached by a free spool. So as tension goes to the right, this inner part is still going to be rotating with respect to R1. It's still going to be rotating clockwise, even though T is going like this. It's still going to be, you know, spinning in a clockwise fashion, because T doesn't. If you took out friction, T wouldn't cause this inner part to move this way. And that's essentially why that tension provides this clockwise torque. And I know it's a bit tough to see, but that's pretty much the reason why. The torque provided by tension is clockwise, and that's why it's negative. But anyway, yeah, that once we get this expression, we, you know, it's all a matter of algebra to solve this guy out. So before, when you set up your equation, did you get 2 positives? No, friction is counterclockwise. So this is the expression that we start off with right here. Yeah, well, you had t as negative. You mean you had a different sign. It should work out itself. It should work itself out mathematically, but this one was a bit odd, only because the tension is arbitrarily applied to the middle, but the whole thing is going to be moving as one. So as R1, so the whole system moves to the right. The R1 is going to be clockwise, even as friction is left alone, is going to spin it counterclockwise. Because friction is actually going to be, so the difference is, as we wrap up today, so the difference is, like, if we had a pulley and we had two strings, both of them will independently provide a torque on the outside. So this torque would be causing the system to go counterclockwise, whereas this one would be clockwise, because they're on the external part of the wheel, so they could have an influence, a direct influence. T doesn't really have a direct influence to cause a different spin. So even though it's applied here, it's still providing a clockwise torque. Whereas here, friction is going to be, it's left alone, it's going to cause this wheel to spin counterclockwise. So we'll take another look at this one next time, but I'll give you some other homework that's a little bit easier, but we'll take another look at this one. All right, that's it for today. We're at 2:20. Do I need to see anybody after school? Makeup skills tests? Yeah, we'll take another look at 85, most definitely. Okay, see ya. Anybody else? Okay. You too. Yep. See you Monday, I think. So Christian, what's going on? You said you were some things were going on in your family? Or are you here? All right, see you later.